Alright, today we are going to talk about the chapter 10, basically the topic 10.3, which is the deviation of actual vapor power cycle from the ideal cycle. So in the previous class we talked about the ideal vapor power cycle, right? Basically we saw the efficiency equation, and we did the power analysis for Rankine cycle, which is a ideal cycle, right? So okay, so basically in the Rankine cycle, if we remember, there was four component. Number one was the pump, right? Number two is the boiler, and number three is the turbine, and then number four was the condenser, right? So pump, we saw that it's a isentropic compression, right? Isentropic compression. In the boiler we saw that it's a constant pressure, um, constant pressure. And then we saw that in turbine, isentropic expansion. And then again constant pressure heat rejection. Constant pressure heat rejection, right? So basically these two are isentropic, and then these two are constant pressure. However, in the real case, what is happening? Let's take a look. Okay, so if we draw the TS diagram, then we'll see that basically the actual diagram was something like this, right? So this is 1 2 3 4. However, in the real case, right, so for example the pump, we saw that we in the ideal case we assumed that the pump is isentropic compression. However, due to the irreversibility, the pressure in the pump, or the temperature in the pump temperature in the pump slightly increases. So that increase, basically, if we okay, so that increase will be expressed by dotted. Okay, so this would be the new actual case, right? And then we see that in the boiler, actually it is not a constant pressure um, process. So pressure also drops slightly. However, temperature, we can reach the same temperature, right? And when the turbine is expanding that vapor, due to the irreversibility of the turbine, we see that the point 4 not exactly within the saturated line. So it lies outside the saturated line. So this would be 0.4, right? And the condenser, also there are some pressure drop, right? So condenser is also not a constant pressure process, so there are some pressure drops. So that's basically the actual process, and that's the deviation. You can see these are the deviation from the actual process, right? So what is happening here, the first thing it's coming in the and the pump, it's irreversibility of the pump. Irreversibility of pump. Similarly, due to the irreversibility of compressor, actually, excuse me, this is turbine, okay, irreversibility of the turbine, right? And this pressure drop in boiler is happening, pressure, and then also the pressure drop in the condenser, right? Pressure drop in the condenser, and basically this is actual, and my solid line is ideal. Okay, so that's the deviation between the actual cycle and ideal cycle, right? So I mean, we saw the, like, each of the components, it's not in ideal cases we saw that there is no loss or no irreversibility. However, in actual case there's some irreversibility and losses. That's why the pressure drop is happening, and you know, in the turbine, in the pump, pressure is slightly increasing, as well as in the turbine, we can see that the moisture, the expansion or exit of the turbine, there is no moisture, still it's a superheated vapor. Anyway, so let's take a look at the actual cycle or actual diagram, TS diagram. If we are to draw the TS diagram, then what would look like the TS diagram? Okay, so in the this is the saturation dome, and then in actual cases, again the ideal case would be something like this one, so this would be 1, 2, 3, 4, right? However, we see that in actual cases, we see this difference, right? So this is 2s, actually, excuse me, this is 2a and this is 2s. S means that isentropic and a means the actual, right? 2a, and then it follows the in the boiler, I mean, somehow we can keep it constant pressure. However, in the turbine we see this difference, excuse me. It just right below or right within the saturation dome, right? So basically it will be 4 actual, right? And then this is for isentropic or ideal, right? So in this case, basically this is TS diagram. In this case, what is the work input and what is the work output of that turbine, right? So this is turbine and this is pump, right? So the efficiency expression, isentropic efficiency, eta pump equals to ws isentropic work divided by actual work, right? So isentropic work is nothing but h2s minus h1 divided by h2 actual minus h1. So in the if we have a problem that is talking about the actual cycle, then we have to use this formula to determine that work consumption, actual work consumption, or ideal work consumption. Okay, and then for turbine, similarly for turbine, which is also isentropic, turbine equals to actual work divided by isentropic work. Basically it will be H3 minus H4 actual divided by H3 minus H4 isentropic. So these are the two expressions that we have to use in the math problem. Okay, so that's the expression, or the difference between the ideal and actual cycle. When we have to solve a problem, we will gonna use this two formula. Okay, so now let's move on to the next topic, right, which is the 10.4, how we can increase the efficiency. How we can increase the efficiency. Okay, thermal efficiency of this cycle, or the Rankine cycle. What are the things we could do, right? So we could do basic idea of, like, of increasing the efficiency of any, increasing the thermal efficiency of any of this vapor power cycle or the gas power cycle is that increase the temperature, average cycle temperature. Then we can increase the efficiency. So the first thing, or the basic idea about increasing the temperature of, increasing the efficiency of this vapor power cycle is two, right? So the number one is the increase the average temperature of the cycle, and it will increase the efficiency. And then number two is the decreasing average temperature at which heat is rejected. Increase the TAVG for Q in, right, input, and decrease the T average for Q out. When the heat rejection is happening, then we have to decrease the temperature. We have, meaning that we have to make sure that as much as we can cool down that working fluid. And when it's going to the boiler, or when it's going to the heat exchanger, we have to, like, we have to increase the temperature as much as we can. Now in reality, right, we cannot increase like too much of this one, because some of the component will not be able to handle that high temperature. So let's go ahead and take a look what are the individual component, or what are the modification we can do in each individual component. So the first thing, okay, the number A is that lowering the condenser pressure. How it will contribute to the efficiency. Let's take a look at the TS diagram, right? So in TS diagram, basically we know that, or in ideal case, we have this diagram. So actually I have to do it one more time, it's very steep. Okay, so basically we know this TS diagram, right? 1 2 3 4. However, if we lower down the condenser pressure, then basically that line will look like this, right? And then so this is the lower pressure line. So this line is lower pressure line. Okay, now you can see that if we can decrease the condenser pressure, right? So this is 4 prime, this is 1 prime, and this is 2 prime. Okay, and then basically, I mean, in this case, the the pressure was P1. However, in this case pressure was P1, prime. So if we can see, if we can reduce the pressure at the condenser, if we can reduce the pressure at the condenser, we can increase the cycle efficiency. How? The W net equation, W net equation, we know that this is Q in minus Q out, right? Basically W turbine, work produced by turbine, minus work consumed by pump, which is input, right? So in this equation W net, in this equation W net will increase, right, when the W turbine and W turbine, when W turbine will increase, right? So if we can increase the W turbine, then W net will increase. At the same time, if we can decrease the W pump, then if we can decrease the W pump, W net will also increase, right? So if how and if we can decrease the pump work, right, then we can increase the W net. And efficiency equation, we saw that W net divided by Q in, right? So basically if we can increase the if we can increase the W net, then we can ultimately increase the efficiency as well, right? So again, how the W pump is reducing here, because you can see here it's the pressure is relatively lower compared to the point 2. So point 1 prime to 2 prime pressure is relatively lower than 1 to 2. This is one thing. Another thing is that the condenser so the condenser pressure, when we are reducing the pressure right here in this line, then it's producing the turbine, you can see that WT is WT equals to basically H3 minus H4 prime. In this case, basically it is increasing, the difference is higher compared to the H4, right? WT equals to H3 minus H4. This difference is higher compared to the this one. So that's why turbine work is increasing, right? So the turbine work is increasing and ultimately increasing the cycle efficiency. This is one thing, okay? This is one step we could do or modify in the Rankine cycle to increase the efficiency. Another thing we could do is number B, superheating the steam to high temperature. How? Okay, so basically if we draw the TS diagram again, okay, so in this TS diagram we have 1 2, this is the pressure line, right? So right now we in ideal case, or we saw that in the Rankine cycle, basically we saw that it comes like this, right? So 1 2 3 4. However, if we can increase the temperature, like if we can increase the temperature of the turbine, the boiler output, which is like superheated vapor, right? So then you can see that this is 3 prime and this is 4 prime, right? So this is S T. So the new work, I mean keeping everything constant, the new work, turbine work, WT turbine prime equals to H3 prime minus H4 prime, which is higher than WT, and that one is H3 minus H4. Why? You can see that the temperature difference here compared to the temperature difference here, like in this line, it's higher, right? So if the W turbine work is higher, then ultimately that equation again, net work is increasing, right? So net work will increase if W turbine is increased, while the W pump, while the W pump is it's remain constant, right? So if the W net increase again, the thermal efficiency will also go up, right? Because everything remains constant, right? So this is another way to increase the temperature, or sorry, to increase the efficiency. Now there is a question. Turbine blade has some sort of specific material, right? High temperature material. So if we increase the temperature too much, chances is that turbine blade cannot survive, right? Turbine blade will be destroyed. So that's why we have to limit this temperature. We cannot go all the way to 2000 degree 3000 degrees Celsius, right? So we have some sort of limitation. So far the turbine blade material can handle 620 degree C. So that's the maximum temperature. So we have to make sure that in the boiler output it's coming up to 620 degrees Celsius. I mean, everything evolves. So who knows? There will be some material developed that can handle up to maybe 1000 degree Celsius, right? So 1000 degree Celsius. So in that time we can increase the temperature furthermore, right? Anyway, so this is one step, and then another step, number C, which is the, I think, the last step for the increasing the efficiency, or you know uh, basically increasing the boiler pressure. Increasing the boiler pressure. What is that? So basically, if we excuse me, if we draw the TS diagram, right, then we'll see that initially our TS diagram was something like this, right? So if we increase the boiler pressure, right, so basically everything will remain constant, however we'll increase the boiler pressure. Okay, now you can see that boiler pressure, and we will keep the temperature constant, the same temperature, right? So basically it will look like this. Okay, this is 1 2 2 prime 3 prime 3 4 and 4 prime. So if we increase the boiler pressure, what is happening here? So basically if the pressure of the boiler increases, right, then the boiling point of that working fluid is also increases. Thus it required thus within the less, or by taking less Q in, it will be like, it will generate the steam. That means the T average of that, or average heat transfer on the working fluid from the boiler, it's also increased. So thus the efficiency will increase. So basically the pressure of the boiler, if the pressure of the boiler is increased, which is the dotted line, right, then it decreases the boiling temperature, decreases the boiling temperature. So if the boiling temperature is decreases, that means it can take less Q in. With less Q in, it can like generate the vapor, right, or the steam, right? So thus the T average or the average heat transfer, T average of heat transfer within the boiler, is increased, right? Wow, how the T average is increased. If you look at this this graph, so the average temperature, so T3 prime and T2 prime is higher than T3 and T2, right? If we take a look, so the temperature is obviously is higher than in increased pressure line. Okay, so average temperature is increasing, thus the Q in is decreasing. Again, the same thing. If the Q in efficiency equation, if you keep the W net same and just reduce the Q in, that means the efficiency will increase, right? So this is another way to increase the efficiency. So if we can increase the boiler pressure, then will ultimately decrease the heat in, or the input heat requirement. So and that will help us to increase the efficiency. So just to show you how this cycles is evolving, in 1922 the boiler capacity, the designed boiler capacity or the pressure capacity was 2.7 megapascal, right? However, in today, and the latest state of the art um, boiler can handle up to 30 megapascal, right? So you can see that how this technology is evolving, right? So who knows, maybe after 5 years, after 5 years, or we'll see that 5 years later, then we'll see that this pressure is also increasing, right? So yeah, that those are the way to increase the efficiency of the Rankine cycle or ideal vapor power cycle. So we'll go ahead and solve a math problem based on those techniques. So that's all for today. Thanks for watching this video, and we'll come back with the math problem.